Yeah, good morning and welcome to today's lecture. So this is the 21st first lecture, and today we will discuss again few more recitation topics. So here the first topic is regarding the information content of a message. So we have seen that when there are different events that occur, some events may occur with one kind of probability, or other events may occur with a different probability. So some events may have a higher probability of occurrence, and the other events may have lower probability of occurrence. So based on their probability of occurrence, the amount of information that they carry also varies. For instance, in general, whenever any event that occurs certainly, as written here in the first line, defines there's a definite event. When the probability of occurrence is very certain, we call it as a definite event that carries less information. And next, an event that is less likely, that is uncertain, Such events will carry more information, so we need to talk more about that, or they will have more discussions on that. So here the definite event has higher probability. That means maybe the probability is 1, that will always occur. So that's a definite event. So such events will carry less information. And the events that are not definite, not certain, uncertain events, that means they have a lower probability of occurrence. They may occur or may not occur. In that case, we will have more discussions on that, whether it will happen or not, when it will happen, all that. So in that context, it will carry more information. Okay, so in general, if we have queue messages, they are M1, M2, M3 and so on up to Q number of messages having varying probabilities such as P1, P2, P3, PQ and so on, then the more probable message will carry less information. So this is the general theory. So based on this, we will see some points here. Especially we will see the information content of a message. So based on the probability of occurrence, how can we determine the information content of a message? So we know in general that when we have different events occurring with the different probabilities such as P1, P2, P3, PQ and so on, when we add all of them, all the probabilities, we get a value of 1. I mean the total probability of occurrence of all these events that are emitted by a source. Maybe these are the messages that are emitted by a source, or some events that occur, that will be equal to 1. Now based on this, the IMI is the notation to represent the information due to a message MI that is inversely proportional to its probability. So information content is inversely proportional to its probability. And here, to be specific, information content of message is equal to 0 if the probability is the maximum. So maximum probability is 1. That is a definite event. In that case, the particular event will carry minimum information, or the information content of such a message is 0. The vice versa is also true. That is, if the probability of occurrence is very low, then such a message will carry more information. So in general, probability value will vary between 0 to 1. The maximum value of probability is 1 when we sum up all the probabilities. Then the information carried by such an event or such a message will be equal to 0 or greater than 0. So always it's a non-negative quantity, it's a positive quantity. So we say here IMI, it's nothing but the information carried or the self information of the message MI. So based on these points, as well as some points that we see here, that is, if there are independent events, then the total information content I is the sum of the information content in each message. That is, information carried by M1 and M2, or MI and MJ here, that is almost equal to the two messages, their combined information, or it's also equal to the information carried by these two events separately, the sum of the information carried by these two events separately. So when we see this term, that is the total information or the joint information carried by two events, that is equal to the sum of the individual information carried by those events. As we can relate these two, we get a sense that this should follow something like the logarithmic rule. So based on that idea, and also the observations we made uh, in point 1, 2 and 3, this is a point number 4, but in the previous slides we have seen 3 points. So based on all those, we can arrive at a discussion that information content of a message will be equal to log of its inverse probability. So Pi is the continuous probability of an event I or a message I. So this is the theory behind the information content and its probability, how the information content is related to the probability and why it follows a logarithmic relation. So if that is the question, then you should be able to describe these steps to arrive at this relation, that is information content is equal to log of 1 by pi. So do we have a logarithmic because it always follows this kind of relation. Okay, it's inverse because we know if the event is very definite, then it carries minimum information, and if the event is not so certain, then there will be more discussions and it carries more information. So it always follows a inverse relation. So probability is higher than the information carried is less, and vice versa. As a result, we can combine those two observations here as log of 1 by probability. Okay, now we will move further, that is information content of a message. So here the information content, as mentioned in the previous slide, information content is equal to log of 1 by probability. For instance, we can see that a source emits 5 messages, and these messages may have different probabilities as shown here: 1 by 2, 1 by 4, 1 by 8, 1 by 16 and 1 by 16. In this case, find the information content in each message. How can you find the information content in each message? It's very simple. The idea here is you need to find the self information of every message. For example, this is the first message, you need to find out its information. So information of this particular message M1 is equal to log of log of its 1 by probability. So or minus log of probability. Basically, we are using this equation, information content is equal to log of 1 by probability. That is what represented here. That is log of 1 by probability, but we have a negative sign here. So we have log of probability, because we know the relation log of a by b is equal to log of a minus log of b. So log of 1 minus log of probability. So log of 1 is 0, 0 minus something, log of probability. So we have a minus log of probability, that term here. So that's one bit and so on. So if I ask you the combined information due to all these messages, so you should be in a position to answer this question. So here the question is finding the information content due to each probability or each occurrence of an event or a message. Yes, it's very simple. But if the question is to find the combined probability, combined information content, the total information content due to all these events. So basically that's the sum of all these, right? The information content of all these messages. That's what we have seen in the discussion to arrive at this equation. So if the total information due to these 5 events is asked, then you need to find the information content of all of these individually and then add them together. That gives the total information content. Okay, then also when you talk about the events, we have to find out the average information content of these events. So now we need to consider two explicit cases. One is the independent sequence. For example, a source that emits different symbols where every symbol generated is independent and it does not depend on the symbols generated earlier. That is called as an independent sequence or memoryless source. Such a source that emits independent sequences is called as a memoryless source. The second one is a dependent source or dependent sequence or Markov source. So here every symbol generated by the source depends on the previous symbol that was generated. So we will see how to find the average information content if the source is a memoryless source, or if the source is a memory source or a Markov source. So basically average information content is the entropy. Okay, you see here. The average information content of the independent sequence. So now we are considering the first case, that is, this is an independent sequence. So we consider a sequence of messages. So let this be a long independent sequence. For example, a camera that generates different photos, maybe a video stream consisting of multiple photos or snapshots, or a teletypewriter producing different texts or different alphabets. We assume that those sequence generated are independent. Okay, so now let there be n symbols, for example maybe n photos or n alphabets generated and so on. So these n symbols may be represent, or m messages may be represented as m1, m2, m3, mn and so on. Each have a probability of occurrence P1, P2, P3 and Pn. Please note that these probabilities are independent. For example, the probability of the second message is totally independent. It does not depend on the probability of the first sequence. That's the idea of independent sequence. For example, tossing the coin, I toss the coin for the first time. Of course, it's a very fresh attempt. I may get a head or a tail. I toss the coin the next time, even the next time, the outcome will not be influenced by the outcome in the previous tossing of the coin. So that is an independent sequence or independent event. So we are talking about such events. In this context, how to find the average information content, that's the main discussion right now. So now here M1 will occur P1 multiply n times. Similarly, any message will occur Pi times n. Please note here that we are talking about a sequence of messages, not just one or two messages. We are not talking about individual messages. We are talking about a sequence of messages. For example, an English sentence consisting of many alphabets, or I said a series of photos. Okay, not just one photo, multiple. In that case, each one will have its own probability. Okay, then what's the total contribution of one particular event or one particular message when you consider the overall size of the message? That is Pi times n. For example, if you consider the first event or the first message, its probability is P1. Its total contribution or total probability or its total weightage is P1 times n. For instance, you consider a sentence or a word here, A, B, C, A, D. Here, what's the contribution or what's the amount of information carried by the alphabet A? So carefully notice here that A occurs twice in this word. So its weightage is 2 out of 5, because there are 5 alphabets. Out of these 5 alphabets, A appears twice, so 2 by n times, right? So that's the weightage of this particular message A. B occurs how many times? It occurs 1 by 5 times, right? It's the probability, 1 by 5 is the probability of B, but how many uh, letters are here? There are 5 letters, so n is 5. The probability is 1 by 5 for B. Similarly, for A, the probability is 2 by 5. The length n is 5. So if you consider this idea here for this specific example, Now, what is the contribution of A towards this particular word? That is 2 by 5 times n is 5, right? So that's the idea here. So in this case, n is equal to 5. Probability for one event, it is 1 by 5. So the same event occurs twice, then it is 2 by 5. If it occurs 3 times, 3 by 5, and so on. Okay, now the average information content again for an independent source. Since the information content of ith message is log 1 by probability, in a sequence of length n, its contribution is pin log 1 by pi bits. So in general, pi log 1 by pi is the entropy multiplied by n. N is the total size of the message or total size of the events. Okay. And then the total information content is nothing but the information content of every message. For example, for the first message, its weightage is P1 times n, and the information contained is this weightage log of 1 by probability. For the second message, P2 log 1 by P2 multiplied by n, because we are considering a sequence of messages. Similarly, for all the independent messages, we compute the total here, that is the information content of this message. And now the entropy is nothing but the average information content. So it's a total information divided by how many elements or how many messages are there here. I mean, in the total set of events or total set of messages. So I total divided by n, that is the entropy or the average information content. So when we say average, we usually divide the total divided by number of candidates, right? So here I total comes from here. So again here we have to consider the total size of the events or total number of messages n. So this is a weighted sum. There is always p1 multiplied by n. It is not just p1 log 1 by p1. No, it is p1n log of 1 by p1. Okay, so altogether this information content of every message, when we add up, we get the total information content. So when we divide this total information content by the number of candidates, number of messages, we get the average. Average is nothing but the entropy. So entropy is given by pi log 1 by pi, because you know in I total we have a common term n. So n at the denominator and n at the numerator we can cancel. So we are finally left with p1 log 1 by p1, p2 log 1 by p2, and so on. So that is nothing but summation of all those terms, pi log 1 by pi bits per symbol. So this is the idea of entropy. Okay, now we'll consider an example here. An independent source emits three symbols A, B, and C, and their probabilities are half, 1/4, and 1/4. In this case, find the entropy. So this is an independent source, but all these symbols A, B, C are generated in one stretch. That means first A is generated, B, next C, and so on. This could be one of the possibilities, A, B, C. Okay, then how to find the entropy? So in that case, entropy is nothing but the total information content divided by number of candidates. Or we also know the simplified equation for entropy. Entropy is equal to summation pi log pi. So we do that here. For the first symbol A, pi half log pi, that is 1 by pi. So 1 by half, that is 2. Similarly, pi log 1 by pi for the second message. And similarly, for the third message, we have the pi log pi. So when you sum up all that and divide by the number of candidates, you get the entropy. I mean, in this case, you just need to sum up. So that comes to 5 by 3. It is not again dividing by 3. That is just application of the entropy equation. Entropy is equal to summation pi log 1 by pi. That is, when you compute that, you should be getting around 1.5 bits per symbol. The other method of finding the entropy is you find the individual information content of A, B, C, and then add all of them and divide by total number of messages. Of course, we have a simplified equation for entropy, so we may directly use that. But the entropy can be found using these two equations. So the other method is mentioned in the previous slide. So we find I total divide by n. So that's one method of finding the entropy. Or the direct method is the direct application of the final equation, that is pi log by pi. Okay, now the next concept is information rate. So information rate R is nothing but the product of entropy and the rate at which the symbols are generated, or the number of symbols emitted per second. So many bits per second will be the information rate. So this is the rate of information of the source. So this is the entropy multiplied by number of symbols emitted. You will see a quick example here. A discrete source emits 5 symbols each millisecond with the probability 1 by 2, 1 by 4, 1 by 8, 1 by 16 and 1 by 16. So 5 symbols are given and their probabilities are mentioned here. And one more information is given that 5 symbols are emitted each millisecond. Then first we need to find the entropy and then we find the information rate. So to find the entropy, the minimum data required is the probability. So with the help of probability, we can easily find the entropy. So I think you have already trained how to find the entropy. Just apply the equation here, pi log 1 by pi, and you sum all these entropies generated by each individual message. So that gives the total entropy as computed here. And then you need to find the information rate. Information rate is nothing but entropy multiplied by number of symbols generated per second. At what rate the source produces the information every second. So in the question, some hint you have. So 5 symbols are generated every millisecond. So how many symbols are generated every second? That will be the input data rate. You need to multiply that with the entropy. So that is what done here. So the information rate is equal to the rate at which source emits the symbols per second multiplied by the entropy. So here we have the 5000 symbols per second. So if 5 symbols in 1 millisecond, then how many symbols in second? You just need to confirm that value multiplied by the entropy here. Entropy is 1.87 bits per symbol. So when you multiply, you get a number here. So many bits per second will be the information rate of the source. Okay, so an important point here is this equation, how to find the information rate. So in this case, you need to sometimes you need to identify how to determine the number of symbols emitted per second. For example, in this case, this data is not directly given. So you need to understand if it is 5 symbols in 1 millisecond, then how many symbols in 1 second, that you need to find out and substitute. I mean, the information is not readily available. You need to think based on this idea, that is symbols emitted per second. So you can find out the required data here to substitute in this equation. And next is the entropy. Of course, you may directly use the equation to find the entropy if the probabilities are known. In this case, we know the probability, so we can directly apply the equation to find that. Okay, let us move further. So here I have a question. So this question is from the previous homework. Consider a binary memoryless source and it emits 0 or 1. Since it is binary, of course, it would emit 0 or 1. Then, when will the entropy attain some maximum value? You are given with a binary source, you need to find out when its entropy will becomes maximum. So when we say it's a binary source, there are only two options, maybe 0 or 1. So if 0 is emitted with some probability pi, then 1 will be emitted with the probability of 1 minus pi. Or if 1 is emitted with the probability of pi, then 0 will be emitted with the probability of 1 minus pi. So this is the foundation. This idea is the foundation to solve this problem. Since it is binary, you can think easily. So then, what is the entropy? So right now I am giving you the solution. This was a homework question. So the entropy is what? Entropy is nothing but, for both the symbols, pi log 1 by pi, right? So if the first symbol, maybe 0 or 1, anyone, is generated with the probability of pi or p, so for that symbol p log 1 by p. For the second symbol, it will be generated with the probability of 1 minus p, because total probability is 1. So the second symbol will be generated with the probability of 1 minus p. So that probability log of 1 by that probability. So that gives the total entropy. The question is when this entropy will attain the maximum value. So just you need to, what you need to do is you need to find the different values of p, and for what values of p your h of x becomes maximum. Let us start from 0 itself, maybe, or 0.001. If p is equal to 0.001, then you find this term and 1 minus p, 1 minus 0.001 log 1 by 1 minus 0.001. So what's the value here? So the general observation is we know that when the probability is the lowest, then entropy is maximum. Since there are two events here, maybe head or tail, or a 0 or 1, when this will be maximum. Since there are two events, yeah, it is little not so direct, but you can think about that. The intuition here is both should occur, right? Then you have the maximum entropy. Okay, so we have the solution here. When the probability is 0, you consider in this equation. In this equation, when you make p value is 0, find out what's the value of h of x. H of x will be 0. When the p value is 0.1 in this equation, then what's the entropy value? The entropy, if you compute, it should be 0.46. Similarly, you keep going for different values of p. I mean, you keep increasing the values of p, 0.1, 0.2, and 0.3, and find out what's the entropy. So when you reach, I mean, as you increase the probability from 0 to 0.1, 0.2, 0.4, 0.5, zero point 0.9 and 1, when the probability is maximum, then your entropy is minimum. So now here, when the probability is 0.5, you get an entropy of h of x is equal to 1. So at this point, you have the maximum entropy. So that is the solution for this question. So when the probability P of occurrence of 0 is 0.5, it means the occurrence probability of 1 is also 0.5, because total probability should be equal to 1. P plus 1 minus P is equal to 1. So now, when both the events are equally probable, then we have the maximum entropy for a binary source. So this is the solution for this particular problem. Okay, next, the average information content for a dependent sequence. So Markov sequence. Here, a dependent source is what? Here the symbols emitted depends on the occurrence of the previous symbols, or the current symbol will influence the occurrence of the next symbol. That's a memory source. For example, when you consider the English letters or sentences, every sentence depends on the previous sentence. Or when you consider just words, then every alphabet generally depends on the occurrence of previous one, because English has that kind of structure. So that's a memory source. When you want to write a particular word, you know each alphabet there depends on the previous one. Okay, so that's an example. Okay, now we model such a source by Markov process. That's a memory source. Okay, here we have a Markov source. So a state diagram is given here. It is for a source that emits different alphabets. For example, A, B, C are the alphabets emitted by the source. So this source may emit these symbols A, B, C in this order. For example, initially it may emit A, and next time it may emit A again with a probability of 0.3, or it may emit B with a probability of 0.7, or if it emits B first, then it may emit C next time, that is definite, with a probability of 1. So if it emits B, it means if it emits B first, then next it will be emitting C, that is definite. In case it emits C first, then there is a 30% chance, 0.3 probability that it will emit C again, or there is 20% probability or 20% chance or 0.2 probability that it will emit A instead of C, or from the state C, that means initially it was C, now it may emit B with the probability of 0.5. There are three choices. Even though initially it was C, the next time the source may generate C again, or it may emit A, or it may emit B, and their probabilities are 0.3, 0.2 and 0.5 respectively. So this kind of representation is called a state diagram. Okay, now we can also represent this with the help of conditional probability. For example, for the same given figure, how can we represent this as a in terms of conditional probabilities? Or for this particular figure, write the conditional probability statements of the next states. Then what's the solution? The solution is here. In case, let us assume that K was the initial state of this source, and the it was in state A. At the very beginning, when state number is kth state, its state value was A, or the symbol emitted was A in this state. So now, in the next state, it is k plus 1 state. What's the probability of the state? So you have to look here. Initially it was in state A. Now, in the next state, what's the probability? There is 0.3 probability that the next symbol generated also A. That is what written here. When you know what was the initial state, what's the probability of the next state being A? That is 0.3. Okay. From state A, is there any other transition? There is a transition to B, right? So if the initial state xk was A, then what is the probability of xk plus 1 equal to B? That is 0.7. That is what mentioned here. Next, is there any other transitions from A to any other? No. There are only two transitions. One is A, other one is to B. There is no transition to C from A. So if if the system or the source was in A initially, then next time xk plus 1, probability of getting a C is 0. So that is what written here. Xk is the initial state. Then what's the probability of getting a C in the next transition? Xk plus 1 is the next transition. Then what's the probability of getting C? That probability is 0. So this is how we can represent from the state diagram to the conditional probability. Or you should be also ready to write the inverse. When the conditional probabilities are given, how to write the state diagram? By seeing this mapping method, you should be able to understand that. In case if this is these three statements, conditional probabilities are given, then how to write the state diagram? That's also a question. So it is just the reverse process. Okay, then here one more example or instance here. In case x of k plus 1 is equal to b, then what is the next state x of k plus 2? That is, now we have to look at b. From b, what transitions do we have? From b, we have only one transition, that is to c. So if the current state is b, then the next state we can achieve from b is only one, that is c. From b, we can go only to c. So even if the current state is b, the probability of getting A or transiting to A in the next transition or next state is 0. Even if the current probability is B, then the probability of transiting to B, no, it's 0. If it is B right now, next time moving on to C is very, very definite. So it has a probability of 1. So this is source, if it emits B first, then it will emit C. But if it emits A, then what is the next symbol? It may be either A or maybe B. That's why we have two transitions here, 0.3 and 0.7. In case if the symbol emitted is C first, then what is the next symbol? It may be A with 0.2 probability, or it may be B with 0.5 probability, or it may be C with 0.3 probability. We cannot predict so easily. We just know the probabilities. But in case of B, it is very definite. If the first symbol is B, the next symbol will be always C. Okay, with this, again, you should be able to map between these two, between the state diagram and the conditional probabilities and vice versa. Okay, now we will see a specific problem here. From this figure, what we can understand is there is a Markov source that emits different symbols such as A, B, and C. And when it emits those symbols, we will mark those by different states such as state number 1, state number 2 here, and state number 3 here. Okay, and transition probability is also given. So initially, if we say that this is the first state and it emits A with a probability of 1 by 2, and from this state, next time it may go to state 2 and emit the symbol C with the probability of 1 by 4. Similarly, from this state, it can go to state 3 while emitting the symbol B with the probability of 1 by 4. The same applies to state B. In state B, it can again emit C and come back to state 2 here with the probability of 1 by 2. Or from this state, state number 2, it can emit symbol A with the probability of 1 by 4, and then we call it as a new state 1. Or from this state, it can emit symbol B with a probability of 1 by 4, and then it enters a state that is called state number 3. Similarly, you can check regarding state 3. In state 3, it may emit B and come back to state 3 itself, I mean its original state, with the probability of 1 by 2, or it can emit C and reach a new state, that is state number 2, or from the state 3 it can emit A and go to a new state, that is 1. So these are the transition probabilities since this is a dependent source. Okay. Now, in this case, as I mentioned, the source emits A first, that is indicated by state 1. Then it emits A with the probability of half. That means it is coming back to the same state. Or from state 1, it emits a C here with the probability of 1 by 4 and go to state 2. Or from state 1, it emits B with a probability of 1 by 4 and reach a new state, that is state number 3. So these are the transition probabilities. You just look at the direction of arrow here. That's a transition probability from where to where. Okay. And also we have another term here, that's the initial state probabilities. So initial state probabilities means what is the probability of initially the source is in state number 1 or state number 2 or in state number 3. What is the initial probability? So in this case, it is equiprobable. That means when you start the system, you start the camera or start the teletypewriter to emit symbols, then initially it could be in any of these states. Maybe initial state was 1, the probability is 1 by 3. Or when you just started the system was in state number 2, the probability is also 1 by 3. Or it was in state number 3, probability is also same, that is 1 by 3. That means when you start the system, teletypewriter or a camera, it may emit any symbol, maybe it emits A, C or B, that is mentioned here. If it was in state 1, it emits A, or it was in C, it emits state 2, it emits C, or it was in state 3, it emits B. So that initial probability of generating any symbol or being in any state is same in this case, that is 1 by 3. It could be in any of these states. So that is called the initial state probabilities, and these are called the transition probabilities. These are the transition probabilities from which state to which state, that is a transition probability. And at the initial point when the system is started, what is the state, that is called the initial state probability. Okay, now with the help of these transition probabilities, we can write the tree diagram. So tree diagram will help us in determining the entropy of different symbols in together. Okay, so from the previous uh, diagram, we'll try to write the state diagram as shown here. So we will write the state diagram for the state number 1. So as given in this question that initially the system was in state 1 with the probability of 1 by 3. Okay, from state 1, what are the different transitions possible? From state 1, it can again go back to state 1 with a probability of 1 by 2. From the state 1, it can go to state number 2 by emitting symbol C with a probability of 1 by 4. From the state 1, it can go to state 3 by emitting symbol B with a probability of 1 by 4. This is directly copied, this part of the figure is directly copied from the information given in the previous slide. If you want, I can just go back to show you here. So this is the first stage I have written in the tree diagram. From the state 1, what are the different transitions possible? Going back to state 1 or going back to state 2 or going to state 3. Okay, this path. So what are the different symbols emitted and their probabilities? That is shown here. 1 by 2 or 1 by 4 or again 1 by 4. Similarly, we copy this part in the next part of the figure. That is from state 2, what are the different transitions possible? We just look at the arrow mark going outwards. For example, from 2, you have one more arrow here going out towards 2. And then from 2, you have one more arrow going towards 1. And again from 2 you have one more outgoing arrow towards 3. So these are the different transition probabilities. You just need to copy the symbol and its probability there. Similarly for state 3 you can represent that. That is what shown here. Okay, so initially I talked about state 1. From state 1, what are the different possibilities? It can go to state 1 or it can go to state 2 or it can go to state 3 with these symbols and their probabilities. Okay, now this is for generating one symbol. In case if the system emits more symbols, maybe k plus 1, k plus 2, so many stages are there and it emits different symbols, then how to find out their combined information carried or entropy? To determine that, we continue this tree to the next stage also. So from the state 1, we know what are the different possibilities. That is basically we are copying this part of the figure again here. Okay, 1 2 3. Okay, next from state 2, what are the transitions possible that we have seen? From state 2 it can go to state A with the probability 1 by 4 and reach the state 1. From state 2 it can emit symbol C with the probability of 1 by 2 and reach again back to 2. Or from state 2 it can emit symbol B with the probability of 1 by 4 and reach the state 3. Okay, similarly I told you that from the state 3 there are 3 different transitions possible, maybe generating A, C or B and reaching the state 1 to 3. Okay, just by seeing the outward arrow in the previous slide we can write this part of the figure. Okay, this is entirely for state 1. From state 1 we can have all these possibilities. Further you can extend. If you think that again the source is going to emit one more symbol, that means 3 symbols, then you need to again extend this from state 1. What are the different possibilities? You just need to copy this part of the figure again here. 1 2 3. Okay, from next we have the node 2 here, or the state 2 here. What are the possibilities we already have here? From state 2 we have these three possibilities. We just copy this part of the figure here, 1 2 3. Similarly for state 3, you copy this part of the figure here. From 3 you have all these three possibilities. Okay, then the same process continues. Whichever state you have, that you just need to copy. That is for generating three symbols. Right now we have seen only two symbols. That means from its initial state it generates one symbol here, and again it generates one more symbol here, or here, or here, all these possibilities. Okay, this is for, I mean, this is from one state, state number 1. Similarly for state number 2, from state number 2, what are the possibilities we have? We just see here from state number 2, what are the possibilities? We can generate now A, C, or B, right? That's what written here, A, C, or B. Okay, if it emits 2, initially it was 2, then it is 1, 2, and 3. So basically we are copying this part of the figure here, because that is the same. From state 2, if it was initially in state 2, then the next transitions will be something like this. Okay, we continue the same part here. For example, initially it was in state number 1, then what happens? We know here. If it was in state number 1, then what are the transition probabilities? The same comes here. I mean, it's the same information. Similarly, if it was in state number 2, then what happens? You just need to copy this part of the figure, as I'm indicating here by a circle, again here. Okay, similarly for state number 3, you can write the same thing. So this is for the state 2. Similarly, you need to write for state 3. The same thing follows here. Initially it was in state number 3, then what are the different possibilities? You can just look at the previous figure and copy the same content here. So the transition probabilities may be, states may be 1, 2, 3. Then what will be the next stage? You can copy from the previous line. I mean, the same idea. You need to just refer to the main figure and identify what are the next transition probabilities and what are the different states. Okay, this is one part of the question. That means if you know the transition probabilities, then how can we write the tree diagram? Okay, now how to find the entropy or the information rate of a Markov source? We have seen in the at the beginning that how to find the entropy or the information rate if it is if it is an independent source. Now in case of dependent source or Markov source, how to find the entropy and information rate? So it is a little bit complicated here, the entropy, because we have the transition probabilities and the state probabilities, etc. Those things we need to consider here. Okay, now here the entropy of the source is equal to the weighted average of the entropy of the symbols emitted in each state. Okay, now the entropy of the state I, so I'm talking about the state here. Please make a careful observation here. It's a state, entropy of the state I is HI. Maybe state 1 or state 2 or state 3 and so on. So entropy of the state, any of the state, is equal to probability. That's a transition probability from I to j, from state 1 to state 2, 1 to 3, 1 to 1, and so on, log of 1 by probability. So many bits per symbol. So this you need to compute for all the states it is going to transit. Okay. Next, the entropy of the source. Entropy of the source, here it's entropy of the source, is the average entropy of each state. Okay, how to find that? So the entropy of the source is equal to Pi. What is Pi? Pi is the probability of the source when it was in some state I, multiplied by Hi. Hi, what we find here, that's the entropy of the state. So basically entropy of the source is equal to its initial probability or probability of that source multiplied by the entropy of the state. That's what written here, pi multiplied by hi. So we find hi here, and pi is the probability of the source. So how many sources are there? For all those sources you need to find that. So that is equal to, yeah, pi and hi. Hi is indicated here. Okay, then information rate is equal to the rate at which the source emitted the symbol multiplied by the entropy. Okay, so we'll see a quick example here and complete this discussion. So now average information per symbol. Okay, that is PMI. For any message MI is PMI, it's a probability. That the average information content per symbol in a sequence of length n symbols is represented as Gn. So that Gn is equal to 1 by n summation PMI log 1 by PMI. So now we'll see an example how to find out the entropy entropy of the source and average information content Gi. So I indicates how many symbols you want to study. For example, maybe one symbol or two symbols and so on. Now here, Hi, that is the entropy of the state, is equal to transition probability log of 1 by transition probability. So if you know these transition probabilities, or if the figure is given, then you need to identify from the figure at what are these values. For example, for H1 is the entropy of state number 1. Here, you just need to look at this part. From state number 1 to which states the system transits. For example, from state 1, it will transit to state number 1 itself. Or from state 1, it can go to state number 2 with this probability. Or from state number 1, it can go to state number 3 with this probability, 1 by 4. So that's what you have to just consider here. For all the transitions, you need to find out Pij log 1 by Pij. The transition probability is 1 by 2. Here the transition probability is 1 by 4. It's 1 by 4. So basically you need to find out what are the transitions we have. Here is one transition outgoing, second transition outgoing, and third transition outgoing. So that's what we sum up here. Similarly, for state 2, what are the transitions we have? One transition, second transition, and here the third transition outgoing. And what are those probabilities? That we substitute here and find out the uh, entropy of this particular state. Similarly for H3. So this gives the entropy of each state. Next, we need to find the entropy of the source. That's the second part of the question. So entropy of the source given by this equation, that's equal to Pi multiply Hi for all the states. So we know all the Hi's, H1, H2, H3 we know. And also it is given in the question, what is the value of Pi, that is initial probabilities of every state. That is 1 by 3. So 1 by 3 for A, 1 by 3 for B, or 1 by 3 for C. So when we sum up all this, because we have a summation here, that gives a total entropy of the source. No matter what was the initial state, as we have considered all the states, we get the entropy of the source here. Nextly, we find G factors, that is G1 or G2. In this case, we consider that, or the question says that we need to just consider one symbol, that is, it will emit just one symbol, maybe A or B or C from its initial state. So G1, where the 1 comes from, because it's just one symbol we need to study. And how to find that? Gi has an equation here, 1 by n and other terms. So To find those terms, we have to find the probability of every symbol. For example, probability of A is equal to half and 1 by 3. 1 by 3 comes from, this is the initial state of, this is initial probability. For example, to find A, probability of A, you just, in this figure, you need to find out from where the A is emitted. For example, from the initial state 1, A is emitted with the probability of 1 by 2. Next, can we see any other A? Yes, there is one more A. From where? It is generated from state 2, right? With a probability of 1 by 4. Is there any other A? Yes, there is one more A here. From where it is generated? It is generated from state number 3 here, right? The probability is 1 by 4. So that is what we are going to write here. A is generated, total probability of having A is equal to the probability of A generated from state 1, probability of A generated from state 2, and probability of A generated from state 3. So 1 by 4 here is the transition probability, multiplied by 1 by 3 here is the initial probability of a particular state from where it is generated. Okay, for example, if you consider this term here, we have 1 by 2 multiplied by 1 by 3, because 1 by 3 is the probability of state 1. We know in the question it is given, and 1 by 2 because the probability of that's a transition probability of generating A is 1 by 2. Similarly, this for B and this is for C. Okay, that gives us a combined value. It's a probability of generating A from this source is 1 by 3. Next, probability of generating B from this source. What's the probability? So you need to find out in this figure which states generates B. For example, state 1 generates B. Yes, state 1 generates B here. And next, any other B? Okay, here. State 2 also generates B. Okay, next, there is one more B here. State 3 also generates B. So that is what written here for A, B, and C. Basically, transition probability multiplied by the probability of, initial probability of the state. Similarly, for C, we find out here and substitute in the GI equation. So that gives us this value. Okay, next, this is just for one symbol. If we need to find out for multiple symbols, for example, the number of symbols emitted may be 2. That means it's not just emitting A, B, or C. It may emit AA or AB, AC, or BA, BB.